However, one could interpret this a little differently. One could say, well, maybe all the people who study this can agree that crossing the x-axis does not mean they disappear, but rather it means they're all crowded together in a small little spot and they're not taking up any extra volume, no extra space. What does that mean? Well, if you have a molecule that's moving at all, it takes up a little bit more space than it itself occupies. It has its own volume plus any extra volume that it's moving around in. So in order to occupy no extra volume, there has to be no movement. By no movement, we mean not only does the molecule not vibrate back and forth, it can't move from left to right, it can't go up and down, but the electrons have to stop spinning as well. The electrons have to stop spinning because they can't take up any extra volume. Not only do the electrons stop orbiting, but they also spin on themselves, and so they have to stop. All motion has to stop. That's what crossing the x-axis means. If you can get to the x-axis, it means all movement stops and the gases occupy no extra volume. This is impossible. This is impossible because what are you going to hold this stuff in? Suppose you could get some stuff that it was so cold that it crossed the x-axis, that there was no movement at all. What are you going to hold it in? If you put it in a cup, it's going to be a little warm. If you levitate it, there's going to be a cosmic ray or something that comes by, hits it, and it's going to collide with an electron, and the electron is going to start spinning, and then as soon as you have the electron spinning, it takes up a little extra volume, and if it takes up a little extra volume, you're now warmer, and you're not on the x-axis anymore. You can't get to there. It's impossible to get there. We will never be able to get there. So this is kind of a trick question. Can it cross the x-axis? No, it can't. If it did cross the x-axis, it would mean, one, that the molecules would disappear, or two, the molecules would occupy no extra volume, which means motion has to stop, and we can't do that. Let's do an example question. V1 over T1 is equal to V2 over T2. So we're going to take a balloon and we're going to cool it down. If we did that, we would put our line in here somewhere like that. And so suppose we had a temperature and a volume that was right there. And we cool it down. Well, if we cool it down to something that's above zero, then we should be okay. But we can take a balloon outside on a winter day in Canada, and get below zero. So we could have a temperature in this region, and we would have a volume. Now I don't know what that volume is, but it's something. It would have some volume. It would shrink, but it would not disappear or anything. Let's look at what it would look like from a formula point of view. Let's try this question. Suppose we had a 5-liter balloon at 35 degrees Celsius, and we're going to cool it exactly to zero. Calculate the new volume. Well, in this situation, I'm going to have some volume. By looking at my graph, it's going to be some positive number. However, when I do my math and I plug everything in, 5 liters times 35 degrees Celsius is equal to V2 over 0. And if I do my rearrangement, I end up with my final volume being 0 liters. I start with a balloon, I take it outside that's 0 degrees Celsius, and all of a sudden my balloon disappears. What's worse than that is if I took it out in a day that was minus 10 or something, then I would have a negative sign in there, my volume would turn out to be negative. How do you have a negative volume? Don't hold on to a balloon and take it outside today, because as soon as you go to a negative temperature, you're going to end up with a negative volume, and you're going to be holding on to that string, and when that balloon implodes and takes up a negative volume, it's going to be a little black hole, and it's going to suck your arm and your head right in with it, and you're going to be gone. You can't have a negative volume. There's a problem here. The problem is not with the relationship. The problem is not with chemistry. The problem is not with the molecules. The problem is not with the graph. The problem is whoever chose the starting point for our temperature. Mr. Celsius, if Mr. Celsius existed, Mr. Celsius gave a convenient starting point. He said, the freezing point of water, that's where I'm going to start. Well, if you're in the Bahamas or someplace where it never gets too cold, you would never have to worry about it. But we live in Canada. We live in a lot of different places in the world, and we can get to 0 and negative temperatures. And so we need to choose a new temperature. A new temperature that has a starting point that we'll never be able to get to. We can't have 0 and we can't have a negative for our temperature. So we need to choose a new temperature scale that will never be able to have 0 or negative. Well, maybe a good point to start would be way back here, this spot that we can't get to, this spot where there's no movement, this spot where everything stops moving. And maybe we should start a new temperature scale there. And Lord Kelvin did that. Turns out that point where all motion stops is 273.15 degrees Celsius below 0. And so Lord Kelvin said, well, gosh, if we can't ever get to absolute 0, if we can't ever get to that point, maybe that should be the point where we start our new scale. That way we'll never have to worry about dividing by a negative. We'll never have to worry about dividing by a 0. So he called it 0 Kelvin. Now a degree Celsius and a degree Kelvin are the same size, but they have different starting points. And so we have to convert our temperatures to Kelvin in order to do this question. So how will we do that? Well, we will start with our degree Celsius and add 273.15 to get Kelvin. Okay, so if we're going to convert from Celsius to Kelvin, we have a few examples for us to try here. So for our first one, 32 degrees Celsius converting to Kelvin, well, that's simply going to be 32 degrees Celsius plus 273. And we can perhaps leave off the 1.5 is equal to Kelvin. You can use your calculator to figure out what that is. For our next question, we start with Kelvin and we want to get degrees Celsius. So it's going to be 185 Kelvin minus 273. Going to be our degrees Celsius. And 532 degrees Celsius converted to Kelvin. 532 plus 273. And that will get us to where we want to be. So let's try our question over again. We have a 3-liter balloon at 35 degrees Celsius. It's warmed to 50 degrees. Calculate the new volume. The instructions should press pause. So, if we look at the answer for this, 3-liter balloon at 35 degrees Celsius. So V1 is going to be 3.0 liters. Our temperature is going to be currently in degrees Celsius, so 35 plus 273 Kelvin is equal to the new volume, which I'm looking for, all over the new temperature, which is 50 degrees Celsius. Convert that to Kelvin. And then I end up with 3.0 times 50 plus 273. There's the extended equation for V2, and you can work it out from there.